Most of the questions in quiz 4 were about a contingency table, looking at the home addresses and colleges of students on the course, and a graph about men's 1500 metres world records. The main thing in interpreting the table was to not be confused by the difference between column proportions and row proportions, or the difference between looking at the marginals of the table, the bit of the table in the borders, and the cells in the middle of the table. Yeah. So the first question, of all students completing the quiz, what was the proportion with a home address in the UK? In other words, we're not interested in the colleges, we're interested in all the students, and all we want to know is, out of all these 83 students, how many had a home address in the UK. That's those 46 here. So it'll be 46 divided by 83, which comes out at about 0.55. Of all the students completing the quiz, what was the proportion who were in the College of Humanities and Social Science? This is the same idea, but this time we're looking at the rows rather than the columns. There were 59 students altogether in the College of Health and Social Humanities and Social Science. Out of 83, 59 divided by 83 is 0.71. Of students who have a home address in the UK, in other words, we're looking at this column here, just the students who've got a home address in the UK. What was the proportion who were in the College of Humanities and Social Science? That's 31 out of 46, which comes out at 0.67. Then that's the, if you like, the column percentage for that cell. The next question just asks for the row percentage or the row proportion for that cell of the students in the College of Humanities and Social Sciences. I can't say it. In other words, of those 59 students, 31 had a UK address, so it's 31 divided by 59, which comes out at 0.53. And the next question asks you for effectively the proportion of cases in a particular cell as a proportion of all cases. So students who had a home address in the UK and were in the College of Humanities and Social Science, again, that's 31 students there as a proportion of all the students. So it's 31 divided by 83, which comes out at 0.37. What's the probability that a student picked at random from all the students who completed the quiz would be a humanities and social science student with an address in the UK? The answer is exactly the same. Remember, we can just shift between proportions and probabilities. The probability of somebody picked at random having any mixture of the characteristics shown on the table would just be their proportion in the table. Yeah. Looking now at the scatter plot of the men's 1500 metre world record, this is just a scatter plot with the record times plotted on the vertical axis, going from about 3 minutes 26 seconds up to about 3 minutes 56 seconds, and time in years along the horizontal axis, going from a bit after 1905 up to about, I think that's 1998 or 1999, something like that. What's the approximate time of the earliest world record shown? Well, that'll be this coordinate here at the extreme left, and that looks to be about 3 minutes 56 seconds. Yeah. How much faster was the world record time by the end of the century compared to the beginning of the century? Well, it's that coordinate there. And it's 3 minutes 26 seconds, so there's been a drop of about 30 seconds. Yeah. In one period, there was very little change in record times recorded. When was this? Look how the graph, the line of coordinates kind of flattens out, and it seems to correspond to about a little before the middle of the 1940s to the early 1950s. Yeah. If you were to draw a regression line for this scatter plot, what would it show? Well, if we were to calculate a regression line, it's pretty clear that any straight line that approximately summarizes those points would lie pretty close to all the points, because the coordinates themselves form a pretty straight line. There's a little kind of deviation here where records seem to kind of stall around about the period immediately after the Second World War, and then sort of caught up again, then start to flatten out, and then sort of dive down again. So it's pretty straight. If in nearly 100 years the record fell 30 seconds, it's more or less falling about 3 seconds every decade. Yeah. That's also going to be the average change in world record times associated with each calendar year. If you draw a regression line, it will just show you for a unit change in X, in other words, for a 1 year difference, what would be the difference on average of the world record time, and it would be falling 0.3 of a second every year on average. And excuse me, as I've already said, the change seems to be pretty linear, pretty constant. That's an interesting fact, because you would imagine that as athletes got closer and closer to the limit, the rate of progress would slow down, but there's no evidence of that happening. That makes me think, although this is very indirect evidence, that perhaps one of the reasons why the line isn't flattening out, but continued improvements continue to be recorded, might have something to do with doping, stimulants, and drug taking in athletics. But that's a shaky inference from some limited data, but worth thinking about. The regression line in the plot slopes downwards because, by definition, a later record must be faster than an earlier one. That's true. If we were recording something else, the line might go up and down. But since, by definition, a record's got to be an improvement on a previous record, unless there's some kind of change in the definition of what constitutes a record, then the line must slope downwards. The scatter plot does show a close association between the date the record was achieved and the time of the record. It's almost a perfectly straight line. Yeah? The correlation between ice cream sales, drownings, and robbery, well, we've gone through this in the lecture. It's nothing to do with any correlation at all between any of these three things. It's about the way in which they are themselves a function of, amongst other things, good weather. In good, sunny, warm weather, there's more people around, out and about, easier to rob. If they're out and about, their houses are also easier to rob. Hot, sunny weather, people go in for a swim in lakes or the sea, and some of them, unfortunately, will drown. And hot, sunny weather, people enjoy ice cream. But we cannot say that eating ice cream makes you drown or commit robbery, or that robbers enjoy swimming and all the rest of it. Frequency table looks at one variable, and a contingency table looks at two or more variables. You can have as many layers as you like in a contingency table, so it is possible to show 3, 4, or 5 variables. Much more than that, and the table gets really a bit complicated and difficult to understand. Either a frequency table or a contingency table can show proportions or counts or percentages, any consistent way of showing the data. A frequency table only ever looks at one variable. It looks at the frequency distribution for one variable. If there's more than one variable in the same table, it's not a frequency table. A scatter plot does show the association between two continuous variables. Our men's 1500 meters world records is effectively a scatter plot. Phi always takes a value between 0 and an absolute value between 0 and 1. It can't take a value greater than 1, simply because it uses the scale of 0 to 1 to express how strong or weak an association is. You can't have causation without correlation. If something causes something else, then the two things are going to be related, and if you measure them, you'll find a correlation. Unfortunately, the reverse isn't true. Correlation is not necessarily an indicator of causation, because two things can be correlated because, in fact, they're both a function of or caused by a third thing, as we just saw with the ice cream robbery and swimming and so on. If two variables are associated and one of them happens before the other, we can't definitely conclude that there's a causal relationship between them. One counterexample would be, say there's an abbey or a nunnery where the monks or the nuns get up an hour before sunrise to pray. There'll be a perfect correlation between their prayers and sunrise, but unless you were particularly religious, you're unlikely to attribute the rise of the sun to the effect of their prayers. So just because something happens before something else doesn't mean it causes it. On the other hand, as question 19 explores, a cause can't come after an effect in time. If we had that, you would effectively have the equivalent of a time machine, if you think about it. So we can't have effects of causes that are still to happen. No matter how powerful our statistical tools are, we must have a strong theory to show causality. You can't infer causal processes purely from statistical results. You need some kind of reasoning about why a correlation might be evidence also of some kind of causal relationship. And that comes from our ideas about the world rather than just the measurements that we make of it. Okay, I hope most of you did very well in the assessment quiz. If there's anything you're still unclear about, just send me an email.